1 minute ago, the floor of the Philippine Trench ripped open, 900 kilometers long, 12 meters high. In that instant, the ocean itself became a wall, surging towards 7 nations without mercy. Over 1 million lives now hang in the balance. And what I need to tell you is this: what if this was not a warning? What if this was a preview of something that's coming? The answer begins where the pressure never truly stops. Beneath the calm surface of the Philippine Sea, the trench stretches for nearly 1,000 kilometers, silent, restless. Along its length, the Earth's plates are locked together, refusing to slip. I've spent my life studying how systems behave when they're stressed to their limits. I've looked at locked faults, analyzed tectonic pressure, tried to understand the mathematics of breaking points. What's happening beneath the Philippine Trench right now is a masterclass in how planetary stress can accumulate silently, invisibly, until the moment of rupture arrives. And I want to walk you through the physics of what happens when that moment comes, because this isn't theoretical anymore. The conditions for this scenario already exist. Each year, the plates beneath the Philippine Trench strain against each other with a force that's almost incomprehensible. 30 to 48 millimeters of stored motion annually, among the fastest rates on the planet. In the north, near Taiwan and Luzon, GPS surveys confirm the crust is wound tight, accumulating pressure with every passing month. The central segments west of Luzon add another 24 to 36 millimeters per year. The southern reaches off Mindanao and Palawan gathers strain at up to 28 millimeters annually. The numbers are small, but they're relentless, a hidden wall of energy, invisible above water, building toward a single breaking point. Think of it like this. Imagine you're slowly stretching a rubber band, millimeters at a time, year after year. The rubber band gets tighter and tighter. The tension in the material grows. You can't see it happening. The rubber band looks normal, but underneath, the molecular structure is being stressed. Energy is being stored. And then one day, something shifts. The structure of the rubber band changes, and it snaps. That's what's happening beneath the Philippine Trench, except instead of a rubber band made of molecules, we're talking about planetary plates made of rock. And instead of a small snap, we're talking about a rupture 900 kilometers long. Yet this growing hazard remains obscured. The network meant to watch over these depths is fractured. For over 3 years, the nearest deep ocean tsunami sensors, DART buoys 52405 and 52406, have been dark, offline, not transmitting. This leaves a detection blind spot more than 400 kilometers wide. No real-time confirmation can come from this stretch of ocean. Instead, the pressure mounts in silence, unrecorded by the sensors designed to warn the world. This is what troubles me most. We have the technology to monitor these systems. We have the scientific knowledge to predict where ruptures are likely. But the infrastructure that would catch the signal, that would give us precious minutes of warning, it's incomplete, it's offline, it's broken. When the trench finally gives way, the first sign may not be a signal. It may not be a warning on a dashboard. The first sign may be the surge itself. People will see the ocean rise and they'll already be in danger. At 10:47 in the morning, the locked plates beneath the Philippine Trench finally break. A rupture slices through 900 kilometers of fault, longer than the distance from Manila to Hong Kong. The seafloor lurches upward, lifting a slab of ocean floor 12 meters high in seconds. This is not a slip. This is not a stagger or a gradual adjustment. This is a hinge. The entire seafloor bends, pivots upward like a massive door opening on its edge. The water above is thrown upward, not swept aside. The numbers are almost beyond belief. Magnitude 9.3, a seismic moment that rivals the largest earthquakes ever recorded. In the language of modelers, this is a full-length finite fault rupture, 900 kilometers long, 120 kilometers wide, average slip near 20 meters, peak displacement at the shallowest edge where the trench meets the continental shelf. The uplift is sharpest where the trench is closest to land, focusing energy straight at the coast like a lens focusing sunlight. The hydrodynamic models tuned for rapid vertical motion warn that this geometry creates a wave unlike anything in living memory. The initial crest forms within moments, its height and speed driven by the abruptness of the uplift and the sheer scale of the moving fault. There is no time for warning buoys. There is no time for distant sensors to catch the signal. The ocean surface forced upward along the rupture line becomes a wall. Its front steep, its energy concentrated, its arrival measured not in hours but in minutes. I want you to understand what this means physically. In the 2004 Sumatra earthquake, the seafloor shifted mostly horizontally. The plates lurched sideways. The tsunami that resulted was devastating, but it spread out as it traveled. It took time. Coastal communities sometimes had 15, 20, even 30 minutes of warning before the first wave struck. In the 2011 Tohoku earthquake in Japan, again, the motion was primarily lateral, a long rolling surge toward shore, devastating, but not entirely without warning. The mechanism beneath the Philippine Trench is fundamentally different. The seafloor rises vertically, not sideways. This vertical motion is called hinge uplift. Professor Fumihiko Imamura of Tohoku University describes it as lifting a door on its edge. The water above is thrown upward. The result is a wave that is steeper, taller, and far faster than waves generated by lateral slip. Hydrodynamic simulations show that a vertical displacement of 12 meters can produce a tsunami wall with a face so abrupt it arrives at the coast before distant sensors can register its true height. Professor Kenji Sadaki, a leading tsunami scientist, explains that with vertical ruptures, the warning time shrinks to just minutes for the nearest shores, sometimes less than minutes, sometimes seconds. The crest forms directly above the rupture, races outward, its energy concentrated in a narrow front. Unlike the low rolling surges of past events, this wave stands almost upright. Its force focused and immediate. Existing warning systems designed for the slower build of lateral quakes struggle to keep pace. The physics of hinge uplift means that by the time alerts are issued, the water may already be at the door. The physics means the system was built for a different threat than what's coming. Within seconds of the rupture, the seismic network catches it. Seismic stations across Luzon and Mindanao record a violent, unmistakable spike. The Philippine Institute of Volcanology and Seismology receives the first raw seismograms at 10:47 and 21 seconds in the morning. In the control room, analysts track the waveform, a sharp onset followed by a sustained high-amplitude shaking that persists for nearly 3 minutes. Automated algorithms flag the event as off-scale. Magnitude readings climb past 8.5, then 9.0, then they keep climbing. At the United States Geological Survey in Colorado, the global network converges on the moment tensor solution. Calculations from dozens of stations confirm the rupture's geometry. A thrust event dipping west with a fault plane nearly 900 kilometers long and an average slip of 20 meters. The numbers match the worst-case parameters. Meanwhile, tide gauges along the Luzon coast register a sudden vertical jump. In Apari, the sea level rises by over 2 meters in less than 60 seconds, far faster than any tide or storm surge. The data is transmitted in real time to PVOLCS and the Pacific Tsunami Warning Center. There is no artifact, no instrument drift. The spike aligns perfectly with the predicted arrival time from the seismic model. Within 4 minutes, PVOLCS issues a bulletin stating that a magnitude 9.3 earthquake has occurred on the Philippine Trench. Instrument cross-checks confirm a vertical displacement event. Immediate evacuation is advised. The United States Geological Survey and the Japan Meteorological Agency independently verify the event. Their bulletins echo the same figures. The chain of data, from seismogram to moment tensor to tide gauge, removes all doubt. The ocean floor has moved. The crisis is real, but here's where the system breaks. Here's where human judgment fails. At the Japan Meteorological Agency, forecasters review their segmented rupture model. Their model assumes bathymetry smooth, energy divided across fault lines. They run their simulation. Their official advisory holds at 3 meters, a figure anchored in decades of historical wave records. 3 meters, manageable. People can shelter in place. At the Pacific Tsunami Warning Center, analysts run a different simulation. Their inputs weigh the full 12-meter vertical uplift. Direct, impulsive. The result is a projected wave crest up to 10 meters with the first surge reaching Manila Bay in under 15 minutes. 10 meters, total evacuation required. Internal messages fly between agencies. The Japan Meteorological Agency forecaster insists, our segmented model fits the basin shape. 3 meters is the advisory. The NOAA team replies, the vertical wall is real. 10 meters is possible. We must prepare for the worst. Each side defends its grid, its assumptions, its urgency. Emergency managers in 7 countries wait for one number. The difference is not academic. A 3-meter warning means shelter in place. 10 meters means total. Evacuation. Millions of people gone from the coast in minutes. But which number is right? The clock runs down as the world watches, caught between models, with the truth still racing across the sea. Within minutes of the rupture, the true scale of exposure comes into focus. Along the low-lying districts of Manila and the crowded suburbs of Novetas and Malabon, 1.2 million people find themselves inside the projected inundation zone. The numbers are not abstract. Each block, each street is mapped against flood models that show water reaching up to 8.5 kilometers inland. At the heart of this zone stands Manila's main port, a lifeline for the country's economy and emergency response. The port's aging quay walls, built for storms and tides, not for vertical tsunami impact, are now the first line of defense against the wall of water moving at highway speed. Port engineer Atmaja has warned for years that these structures cannot withstand a sudden surge above 8 meters. His reports, often overlooked, detail the risk of total quay collapse, container avalanches, the paralysis of rescue logistics. He warned. Nobody listened. Now the warning is coming true. Across 7 nations, similar warnings flash through emergency channels. Each coastline, each port faces its own reckoning with a force that cannot be stopped or delayed. The ocean itself has become the message. 12 meters of vertical displacement, 900 kilometers of fault rupture, a wave racing towards shore faster than information can travel. The system that was supposed to protect people is now paralyzed by conflicting models. The infrastructure that was supposed to monitor the threat is offline. And the people living on these coastlines are facing a physics they cannot outrun. This is not speculation. This is not a worst-case scenario we can ignore. Right now, over 125 million people live within reach of the Philippine and Manila Trench fault lines, with key tsunami sensors still missing in the Western Pacific. Every minute of warning counts. Every minute we're blind. Every minute the pressure continues to build beneath the seafloor. The numbers keep accumulating, 30 to 48 millimeters per year, the plates grinding against each other, the stress mounting, silently, invisibly, until the moment when silence breaks. The ocean remembers the pressure we ignore. The trench stores the energy year after year, millimeter by millimeter. One day the rubber band will snap. One day the locked fault will rupture. One day the ocean will rise and become a wall. And when that happens, the difference between models, between warnings, between seconds, will mean the difference between survival and catastrophe. The science is clear. The risk is real. The question is, are we paying attention while there is still time to prepare?